So to get these gas phase mole fractions for CS2 and sulfur, we need to go through the material balance analysis for both these species. Okay? All right, so we'll start with sulfur. Remember, we're treating this system as an open system. So we have input and output, and we do have a reaction, right? But when it comes to the sulfur, it's on the reactant side, so nothing's really going to be generated for it. And also, when it comes to accumulation, we assume steady state. And so in the end, our material balance just simplifies down to, well, I'll write it like this. The output is equal to the input minus the consumption. Okay? All right, so for the input, it's just N1S2. For the output, it's N2S2. And for the consumption, it's going to be the magnitude of the stoichiometric coefficient for the sulfur times the extent of reaction. In this case, this magnitude is going to be 1 mole per second. Okay? All right. So, from our material balance, we get that N2S2 is equal to N1S2 minus psi. Okay? All right, so we'll call that equation 2. We can now relate the moles coming out of the reactor to the moles coming in and the extent of reaction. Let's now move on to CS2. Steady state. It's being generated, but it's not being consumed. Also, we don't have any input. So the output is just equal to the generation. Output will be N2CS2. Generation will just be the magnitude of the stoichiometric coefficient times psi. This one's also 1 mole per second. Okay? So we find that N2CS2 is equal to psi. All right, so we found ways to describe the molar amounts of sulfur and CS2 as a function of the extent of reaction. But for the equilibrium constant, what we need are the mole fractions, the vapor phase mole fractions, okay? Or gas phase mole fractions. So if we need gas phase mole fractions, we need to figure out the total amount of moles just in that gas phase. So N2 gas, so only the gas, right? We don't care about carbon at this point. So in the gas phase, we have the moles of sulfur and the moles of CS2. And based on our material balances, we could write them like this. Right. And so the size will cancel. And the total amount of moles is just going to be equal to N1S2. Okay? So just to emphasize, only care about gas phase species for YI. Okay? All right, so now that we have the total molar amount, we could write equations to describe the mole fractions. So the molar amount of sulfur coming out divided by the total moles in the gas phase. Same thing for CS2. It's going to be psi over N1S2. Okay? So we have one way to describe the equilibrium constant here. Right, and we can relate it to the mole fractions. But what we also have to remember is that we want to see how this equilibrium constant changes as a function of time. Okay? Right? And Also, right now we don't know K and we don't know psi, so we're going to have two unknowns in that equation. So mathematically, we need another equation in order to describe, in order to solve for all the unknowns. Okay? And that other equation we're going to use has to do with the thermal or the temperature dependence of the equilibrium constant. So as we saw in the video lectures, not only can we describe K based on the activities, we could also describe it as a function of temperature using this equation. T minus 1 over T, all right, 298, the standard state sort of temperature. Okay, so we could use this equation to calculate K. To get K naught, this is where we're going to use our Gibbs energy of the reaction, so negative G reaction over RT, 298. Right, and so when doing this calculation, be careful with your signs because delta G itself is negative. Negative 12.9 e to the 3. Also be careful with your units. So that's going to give us joules per mole. We'll divide by R. Divide by T298. So we get that K naught is equal to 182.5. That's unitless. All right, so we want to look at two different temperatures, 750 and 1000. We'll start with the 750. Just like with most equations that you use as a chemical engineer, for the temperature, you need to use absolute temperatures. So 750 degrees Celsius is 1023 Kelvin. So we're just going to use this equation. So we have that 182.5 times the exponential. Same thing here. Be careful with your signs. Negative 10.8 e to the 3 joules per mole. 8.314 joules per mole. K. Then we're going to put 1023 K minus 1 over 298 K. Okay, and what we get is that our K, 1023, is equal to 8.31. Okay, so now we figured out what K is, and so now that we know what K is, if we relate this equilibrium constant back to the activities, we'll now only be dealing with one unknown. So we could replace these mole fractions with the equations we derived up here. So psi N1S2 divided by N1S2 minus psi divided by N1S2. N1S2's cancel. We get psi over N1S2. One equation and one unknown. So if we solve for psi, we got 0.89. Okay? All right, so about 89% of the sulfur is, because we're using 1 mole per second, this means about 89% of the sulfur is consumed, right? All right, so now what we want to do is we want to calculate that fractional conversion. We had this equation before, sort of a general one. But what we could do now is we could also plug in our equation for N2S2, and when we do that, all we're left with is just this. Okay. So we'll plug in the 1 mole per second divided by, or multiplied by 0.89 divided by 1 mole per second. And so here, yeah, our fractional conversion is 89%. Okay, so this tells us that 89% of the sulfur is consumed when we're at a temperature of 1073, or 1000, should be 1023 actually. All right. Oops. 1023 Kelvin. Okay? All right, but now what we want to look at is we want to see how the conversion changes when we go to a higher temperature. Okay, so we're heating it more. We want to see how that conversion changes. Okay. All right, so to do that, we're just going to follow basically the same steps we did at the lower temperature. So first, convert to absolute temperature. So 1000 degrees Celsius is 1273 Kelvin. Plug into our equilibrium constant temperature equation. Negative 10.8 e to the 3 joules per mole. 8.314 joules per mole K. Here I have 1273 K minus 1 over 298 K. What we get is now we see our equilibrium constant went down from 8.3, now it's down to 6.5. All right, once we have that equilibrium constant, we'll relate it back to the activities and consequently the extent of reaction. S2 minus psi divided by N1 S2. Let's cancel. And again, we're left with psi over N1 S2 minus psi. So nothing changes with that equation. The only thing is now the equilibrium constant is smaller. So if we solve for psi, we get that it's now equal to 0.866. We could then calculate the fractional conversion, which is still just equal to this. 1 mole per second, 0.866 divided by 1 mole. We get that the fractional conversion has now decreased as we increase temperature. Okay? That may be a sort of non-intuitive result. Typically, we think that if we increase the temperature of something, reactions happen faster and more is able to react, right? But the key to this is to look at the signs of, or to think about the type of reaction that we're dealing with. Here, our delta H is negative. So this tells us our reaction is exothermic. Right? So just like you learned in General Chemistry 2, right? When something is exothermic, essentially the way you could think of it is that heat is one of the products, right? Or hotness is one of the products. Okay? And so if we increase the temperature of our system, what we're doing is we're adding more heat to the system. So as a result, based on Le Chatelier's principle, that's going to push the reaction more towards the left-hand side. Okay? All right, and so by increasing temperature, we shift the reaction to the left-hand side, and as a result, we find that our equilibrium constant decreases. And consequently, that's going to lower our conversion. Okay, and so with this problem, basically it was an example of how we could use our sort of activity coefficient equilibrium constant framework in order to analyze a equilibrium reactor system.